The first problem is a particle moves along x-axis under the. Do you all have the recitation right? Did you get from LMS?
Yes sir, आ गई है.
Good. So the first problem is the particle moves along x-axis under the influence of conservative force with a potential energy U of x, a potential energy function. The figure below shows the plot of U of x versus x. The figure also shows several alternative energy levels. Well, instead of reading all the question, let me just take you to the main thrust of this problem. So this time, instead of giving, usually you're giving a functional form, okay, of potential energy. For example, if you were talking about the potential energy of a spring force, so the potential energy, usually the functional form U of x is equal to half kx squared. Okay, if you're talking about the potential energy due to gravity, then the functional form is mg y. You see, potential energy has some way of depending on the position. In this case, linearly. In this case, quadratically, it can have very different dependencies. For example, potential energy due to a Coulomb charge, for example, due to a charge on another charge particle would be something probably like U of r with some constants. So it would be 1 over r. So you can have various position, potential energy can have various different dependencies on position. In this case is 1 over r, this case is y, in this case is x squared. Okay, and what we have here is a potential energy function. Okay, once we know this, we can find out the force acting on the particle. Okay, so let's say a particle is subject to this potential. Okay, so what would be the force? Anyone, please? Any ideas? How do we get force from potential? Yes, please.
सर पोटेंशियल एनर्जी आपकी जो होती है इट प्रोड्यूसेस, मतलब उससे एनर्जी प्रोड्यूस होती है ना, तो इस वजह से उससे आपकी फोर्स भी प्रोड्यूस होगी कॉन्सिक्वेंटली, आई थिंक.
Yes, that's we know. Okay, good. But how do we get it? How do we calculate force?
Differentiate करेंगे.
Differentiate करेंगे. Negative of the derivative. Negative of the derivative of U gives us the force. Okay, and you will see why negative. Okay, let's apply this here. Okay, we apply this to this potential. What is the force we get? Take the derivative. What is the derivative of half kx squared with respect to x?
Kx आ जाएगा.
Kx, and then this minus here. Okay, now let's make a plot of both. So what is the, how does the potential energy look like? This is x. Yes, and this is U of x. So it would be 0, and then it would be a parabola, right? That is how the potential energy looks like. Okay, how would the force look like? Any ideas?
Straight line हो गई सर.
कांस्टेंट चेंज करेगी ना, as in it has a constant relation.
Yes. So किस तरह की स्ट्रेट लाइन होगी? यहाँ पे किधर होगी? इस हिस्से में इधर होगी, ऐसे होगी, किस तरफ होगी?
सर आई थिंक सेकंड और फोर्थ क्वाड्रेंट में उनकी नेगेटिव है ना, नेगेटिव kx.
तो फोर्थ क्वाड्रेंट में होगी ना?
सेकंड में भी तो हो सकती है.
हाँ बिल्कुल बिल्कुल, ये ठीक है. ऐसे ठीक है, इस तरह की फोर्स है, that's F spring, ठीक है, that is related to this potential energy through this derivative. All right. What is the meaning of this negative sign? Hmm? What is the meaning of this straight line? So what is happening is, now let's analyze this further. Okay. When you are on this side of the, let's say that we set the origin at the mean position where the potential energy is minimum, okay, or the force is 0. Okay. You see, the minima of the potential energy coincides with the force being 0, okay, and no surprise because they're related through a derivative. Once you are on the right side of this coordinate on this position, the sign of force is negative. That means the force is acting in this direction. Okay, and it makes sense because particle is climbing up. Okay, its potential energy is rising. Okay, and once you are on this side of the this mean position or the equilibrium position, the force is in this direction. And the magnitude is same always. If you are, let's say, one centimeter away from the mean position on this side, and if you're 1 centimeter away from the mean position on this side, the magnitude of the force is the same. And the minus sign is only indicating that it's acting in different directions. So the force changes sign at this point, at the minima. So the particle goes in this way and it starts pulling it back. Particle goes in this way, it starts pushing it back. All right. Now let's say that we throw in a particle into such a potential or initiate a state. You can initiate a state by pulling on a spring mass system and then releasing it. Or if you have a pendulum, you just push it on one side and leave it. So you're providing external energy to the system. So it means you're providing some kinetic energy initially. Okay. Let's say that the energy that you initially provide to the system, if it is a pendulum, okay, you know that pendulum has this type of simple harmonic motion. Let's say it's a spring, okay? Let's not confuse it with pendulum. So let's say it's a mass spring system, okay? And you have a block here at equilibrium position, okay? You pull it a certain distance. You pull it from here and you bring it here and you hold it for a second. So what is its potential energy here? Let's say that this position is x naught. Okay, so its potential energy is half k x naught. All right, sorry, half k x squared, x naught squared. That's its potential energy. Once you release it, now what is its total energy now? The total energy E is the same as the potential energy because there is no kinetic energy. You're holding it. You're holding the spring at x naught. Okay, the mass spring system. Once you release, now force is acting on this in this direction. It accelerates. Okay, it accelerates. Okay, and when it reaches here, what is its potential energy now? What is the potential energy?
0.
0. What is its kinetic energy?
Half kx naught square.
Almost the same, okay? Because all the potential conservative force, all the force would have gone to the kinetic energy, okay? All the potential energy. But what about the total energy? Hmm? What about the total energy at this point? Or at any point on this graph?
The same
So
रहेगी.
same रहेगी. So the kinetic energy plus the potential energy makes total energy. As the particle's potential energy decreases, its kinetic energy increases. And its kinetic energy is maximum here when the force is 0. because you are accelerating, you get the maximum kinetic energy because your speed, your velocity is maximum. Once you turn on the other side, the force starts opposing your motion. You're moving in this direction, but you're climbing up the potential energy curve, okay? So the force starts decelerating, this force. It decelerates when you go in this way, then you get to rest, zero velocity here. They should be equal, so I'm sorry. Let's say at this point, you get up to here, all right? And minus x naught, okay? And then once you are here, your velocity is zero. Your kinetic energy is zero. Your potential energy is maximum. Then the force again starts accelerating it. The total energy remains this graph, this. The sum of the kinetic energy and the potential energy is always constant. Only if the force is conservative. So no energy is being dissipated or going anywhere. So the energy you put in the system initially remains in the system, ignoring friction. All right. So then these are turning points. What are these points? Turning points. Because it cannot go further than that. If its total energy is given by this line, if that is constant, let's call it E or E1 or whatever you like, then on the potential energy curve, the particle cannot go up here, okay? Because that would break this equation, all right? That would mean that you have negative kinetic energy. You cannot have negative kinetic energy, remember. You can only have this quantity negative, either mass is negative, which we know is not the case, or the velocity is imaginary. That's not the case, okay? The speed is imaginary. So kinetic energy cannot be negative. Okay? So these are turning points. And if your system has this initial energy in this potential, this is a bound orbit, if you like. Okay? It would always stay there. This particle cannot escape with this much total energy. Would always stay in this potential. So that is more or less the concept behind the problem that we are trying to solve. Okay, it's a very interesting problem. And instead of giving you an exact expression like this, you are given just a graph. Okay. Now let's make the graph and analyze the situation. Okay. So the potential energy is something like this. This is U of X, and this is X. Okay. And it looks like something like this. Okay. So that is the potential energy curve. And you see the potential energy can be negative. It is negative in some region. And here are the given energies. This is one energy that you have, E3, according to your notes. Then we have another energy. Okay, another energy, E2.
Sir, the white one is what energy again?
The potential energy curve, U of X. Okay.
Okay, thank you.
And the blue is the total energy. Okay. all right? And then we have E1. Okay. So we have three different given situations. Okay, three different given situations. And if you're wondering, let me just give you an example, or let's just analyze it. Okay, so this is your total energy. Now, can you identify the turning points?
जैसे E1 E2 E3 की जहाँ पे इंटरसेक्शन होगी वो टर्निंग पॉइंट्स हो जाएंगे।
E3 की बताएं, E3 के कहाँ है टर्निंग पॉइंट्स?
ऐसे ही जो दो कर्व पे जो इंटरसेक्ट कर रहे हैं ना ये है।
बिल्कुल, exactly these are two turning points. Okay, now with this energy, can the particle be here at this position? Is E3 के साथ, if an object has energy E3, total energy, can it be here? Anyone?
सर मैंने
No, no,
सर
it
ये जो
can't.
बोला है कि मतलब डायरेक्शन तब चेंज होती है व्हेन दे इंटरसेक्ट, कि आपको कैसे पता चला?
Sir, the motion of the object will vary between the turning points.
Sorry, one by one.
So it can't.
Amna, please.
Sir, I'm saying that it can't be over that point because the motion of the particle will vary between the turning points, but not beyond them.
Yes, exactly. So the particle would remain trapped in this region. Okay. Okay. Cannot go further than, it doesn't have energy large enough to climb this hill, this potential hill, or cannot go this way because once so here the force is 0. So if you want to plot a graph of force, so this would more or less look like this. Okay, and let's say that this is reference axis. Okay, the force would be 0 at this point, pushing in this direction, and on this direction pushing the particle in this direction. Okay, so once it goes in this direction, it gets pushed back, and on this side it gets pushed back. So this is, what is the question? Where are the turning points? Well, we identify the turning points for this curve. Okay, let's identify turning points for all the curves. What are the turning points for this curve, for this energy?
फिर इंटरसेक्शन कैसे होगी?
This way and this way. Now you see, this is a bit more detailed. So when the particle starts here, it accelerates, okay? It gets some speed, some speed, it reaches some maximum speed, and then it starts decelerating. Its potential energy is increasing. But now it has enough kinetic energy because it has this much potential energy converted into kinetic energy. It has enough kinetic energy to go over this hill. Okay, it has total energy is larger. So, and this is potential energy. So it has this much kinetic energy to roll over this hill and come here, and then accelerate actually, then decelerate very sharply because the potential energy is going very sharply up. So it's a barrier, and it reaches up to this point, and then it cannot go any further because the potential energy is going higher. It has exhausted all its kinetic energy. So these are its turning points. What about this? Quickly, please.
सर बस एक ही होगी टर्निंग पॉइंट।
Only one. What does that mean, by the way?
So I think we'll exclude the top part of the graph and it will include all the rest of it.
We will exclude? No, I didn't get that. So the point here is that, let's say it's
सर E1 के लिए होगा वो एक ही डायरेक्शन में जाएगा वापस जाएगा।
yes, so it's an interesting problem. For example, and these two are, so let's say, so if the particle is coming in with this energy, okay, think of it as a two-body interaction. Okay, so let's say that one body is providing this potential and the other is experiencing it. You can think of it as a potential due to a nucleus on an electron or another atom. Okay, and that's what leads to bonding actually. And which bonds are where you can form stable bonds and where you do not make bonds. Okay, which orbitals lead to bonds and which orbitals do not lead to bonds. Okay, so it's let's say the object is coming in. Okay, it would, and then from here on it would start feeling the force. Okay, it would start feeling this potential. It would accelerate. Okay, it would be faster here, then it would decelerate, would be slower here. Okay, then it would again accelerate and would be very fast here at this point. Okay, at these points it would be fast, at this point it would be slow. Then it, once it starts climbing this potential, its total energy is can only bring it this much. Okay, up to this point, cannot push it any further. All right, and then it bounces back, it comes to rest at this point, then it starts accelerating, then decelerates here from this region to this region, then accelerates from this region to this region, then decelerates, but its total energy is enough to escape this potential trap. Okay, so that's the lesson. So this is not a bound state. These two are bound states. Okay? Another difference you see, when you push two objects together, any two objects, you see that you cannot push them any further. And that is, by the way, that is the shape of the, roughly the shape of the repulsive potential that is acting. So if you bring in slowly, you can get up to this. If you push or hit something very hard, you can get much closer to the object, and you can get much more closer to the object. So this potential, this is the repulsive part of the potential. Okay, another way, whenever whenever you have the sign of the, so the point is that if this is your point of view, okay, if you're standing here at the origin, okay, the negative direction of force gives you repulsion. Okay, so whenever the force sign is negative, it means that is the repulsive part of the potential. You're pushing objects away. And here, or would this be, yeah, the force would be negative. That means you are pushing things away. Okay, is that right? Yes, it's right. And then when the sign of the force is opposite in this region, this is attractive region. You're attracting things towards, you're accelerating things towards yourself, towards the origin, towards this reference point. And you can think of this, for example, these open orbitals, these orbitals, you see them in chemistry, for example, when a particle approaches, the potential does not have this detail in chemistry. It's much more simpler. It goes something like this. But and then you can think of these bound states, but you can also apply this analysis to comets or planets, for example. So let's say that this is the potential, roughly the potential due to, so it's very hard to say that there is any repulsion until you really get to the surface of the surface of sun. But thinking of the problem in a very similar way, that when you have a comet approaching the solar system, all right? So here you have sun. And sun has a potential energy field around it. It pulls due to the gravity on objects. So now let's say you have a comet coming in, okay? If the initial entry and the energy at the energy with which the comet enters the solar system, if it is not large enough, and also depending on what trajectory it is coming along, and if it passes too close to the sun, it can get trapped into an elliptical orbit around the sun, okay? And then it always remains trapped and stays there. So that would be an example of a bound orbital, okay? Then again, sometimes you can have larger energy and given the position, it changes course because the potential energy is acting on it, but it doesn't get trapped. Okay, gets pulled towards sun, changes its course. Its course is being changed because of the sun, and then it leaves the solar system in a different direction. And these are elliptical orbit. These are parabolic, and then you can also have very small amount of deflection, hyperbolic trajectories as well. Okay, so these three graphs tells you that depending on the initial energy, how potential energy can cause different results. All right, read about it. Where the speed of particle is maximum. We have already answered that the speed of particle would be maximum here. In this case, it would be maximum here. In all cases, it would be maximum here actually. Okay, where is the speed minimum? So the speed would be 0 at turning points in all cases, but it would be also very small for this particle here. This particle, of course, its minimum speed is at these turning points. So and is the orbital bound or unbound? So these two are bound and this is unbound. Now go ahead. Somebody wanted to ask a question.
Sir, can you please explain about the repulsive part of potential again?
So if you have a graph, a potential that is like this, okay, let me make axes as well. Okay, U and X. Okay, so what is the derivative here? What is the derivative of this curve here? Just tell me in terms of positive, negative. It's negative. Okay, so the derivative of U in this is negative, and then we have a negative in the formula of force, right? So then force would be positive in this region. समझ आ रही है बात आमना?
Yes, sir. Thank you.
क्योंकि डेरिवेटिव नेगेटिव है और एक नेगेटिव हमारे पास इक्वेशन में है, फॉर्मूला में है, तो फोर्स इस डायरेक्शन में लग रही है. ठीक है, तो एनीथिंग दैट कम्स इन feels this extremely quickly rising force. Okay, that is why objects do not merge into each other, okay, when you push them together, because this repulsive potential comes into play. Okay, it emerges from atomic scale. अब ये देखें कि if you are on this side, the derivative of this curve is positive, but then we have a negative in the formula, so force इस direction में है. तो अगर आप यहाँ से देख रहे हैं, this is your point of view, so this part of the potential, और कहीं से भी देख रहे हैं, तो this part of the potential is repulsive. When you are in this region, the force is trying to send you away from the origin, this point. And if you're in this region, the force is trying to bring you together. So this is the equilibrium point. These are usually, this is how you estimate bond lengths. Okay, when two atoms are bonded together, this distance tells you what the bond length is. That is the equilibrium position. Of course, atom keeps oscillating, vibrating around this position, and they are trapped. The kinetic energy is not large enough. So when you heat up an atom, which is bound to another atom here at origin, then it would have enough kinetic energy to escape this. That is why when we heat up things, chemical bonds break.
Okay, thank you, sir.
Okay, so the next question. Sorry, this is running behind time. All right, so please see the figure in your, I may not be able to draw it as perfectly. Ah, come on. So we have a cube. Okay, a cube of each side L, and then, okay, before I do anything, what is the center of mass of a cube? What is the center of mass of a cube? Each side
The
is
geometric center.
G,
The geometric center, sir.
the geometric center. So if they, if this
That
corner
half
is,
L.
if this corner is at the origin, and this is, let's say, x right-handed, so x, y, if this axis is y, no, this axis is y, this axis is x, and this axis is z. If my origin is at the corner, so what is center of mass then? What is the geometric center of the system? Quickly, please.
Yes, sir. Half LX plus half LY plus half ZY.
Yes, and
LZY.
Lx, Lyz are same. So L by 2, L by 2, L by 2, that would be the center of mass. Okay. But if I choose the origin at this point, at this very point, okay, then the center of mass would be
0, 0, 0.
0, 0. All right. That would be the center of mass for this object. Now, you did not have to do anything because it's a symmetric object. It's symmetric in all directions, in X, in Y, and in Z. All right. Now, what we are going to do is we're going to do a problem where we deliberately break the symmetry, okay, and then try to calculate the center of mass of the remaining object, the object with broken symmetry. So what we are doing is, along x-axis, all right, along x-axis, we cut this cube, we cut a cylinder through this cube, which is exactly of radius r by 4. Okay, so if it is r by 4, then its diameter would be r by 2. Sorry, L by 4, not r by 2. L by 4. We cut this cylinder all across. We take this face of the cube, we choose this radius, and we drill through the whole cube to up onto the other side. Okay. Now carefully look at this. Surely we have broken the symmetry, and this may not be the correct answer anymore. So we want to find out the center of mass of the remaining cube. Okay. After taking this cylinder out. Okay. Now carefully look at it. Would the z coordinate, the z coordinate of the center of mass change? And if it does, how much? Didn't have coffee?
Yes, sir. Z नहीं change करेगा.
Because
क्योंकि थ्रू आउट दी क्यूब के अंदर वो कट किया है ना, तो हर साइड पे वो इक्वली इफेक्ट होगा.
particularly if you cut this remaining cube here in the middle, you have the same amount of mass up above this point and same amount of mass below this point, right? Despite cutting this cylinder. Okay. So in a way, we have not broken the symmetry in the z direction. The problem is still symmetric in the z direction. So z remains 0. All right. How about x direction, which is this one, along the direction of the cylinder?
सर थोड़ा राइट पे चला जाएगा.
नहीं, x is this one. This is x here. We have cut the cylinder in this direction. ये cylinder का axis है. अगर आप क्यूब को यहां से काटें, हाफ करें, तो जितना मास परली तरफ है इतना मास इस तरफ भी है. We have not, x भी change नहीं होगा. Okay. ये y है. Alright. So the only coordinate that would change is y, because if you cut the cube in this direction half from here, then you see on this side you have more mass, and on this side you have less mass because you have taken a cylinder out. All right. So the only thing we need to work out in the problem is this y coordinate. If we can work out the y coordinate of this hollowed cylinder, x and z would still be the 0, and then we would have answered this question. So do you agree with this? All right, so now to solve this problem, what we are going to do is we are going to do this. We take out the cylinder, okay, and we find out cylinder's mass, cylinder's center of mass, all right, which we let's say is this M1, Y1, sorry, is Y1, okay, we call it yes. So let's say that we take out the cylinder and we know its center of mass because it's a geometrical object. We'll figure that out. And let's say that we also know the y coordinate of the center of mass of the remaining cube. Okay. If we take these two objects and we know their center of masses, we can put them together. We can put them together and write this equation. M1, where M1 is the mass of the cylinder and M2 is the mass of the remaining cube, and Y2 is the center of mass, y coordinate of the center of mass of the remaining cube, okay, over M1 plus M2, okay. This would be the y coordinate. If I plug the cylinder back in after cutting, taking it out, if I put it back, okay. So what should be y here?
0, sir.
0, because I've put it back. And then the remaining equation would be M1 Y1 plus M2 Y2. You can do the integration and do the first principles, but we are trying to use a trick. Okay. So now we have this equation. And our unknown is Y2. Y2 is what we are trying to find out. So if we can figure out Y1, and if we can also, you will see how this works out, okay? Now in this coordinate system, where is the center of mass of the cylinder? The coordinate system is x at this point, at the geometric center of this object cube. So what is the y coordinate of the center of the cylinder? That's where, because of this cylinder symmetry, that is where the y coordinate, that would be the coordinate of this center would be its y coordinate of its center of mass as well. Sorry. So what is this point? What is the coordinate of this point?
Minus L
L
by
by
4.
4.
Sorry?
L by
Minus
4.
L by 4 aa raha hai, sir.
Minus L by 4, right? Because here is the origin, eh? Minus L by 4 on this side of the coordinate system. So now we know what is y1, right? minus L by 4. Okay, so what about M1 now? Okay, let's say that M1 plus M2 is M, the total mass of the cube before we cut the cylinder out. All right. So what would be the mass M1? Can I write, let's say that it's a uniform distribution of mass in this cylinder. So the density of this cylinder would be M over L cube, right? Before cutting, M over L cube times the volume of the cylinder. What is the volume of the cylinder, please?
pi r square h हो जाएगा
Volume of the cylinder would be pi
L by
Pi r
4
L.
square.
pi over L by 4. That is the radius, squared times
L.
L. Okay, that would be M1. All right. Then if you simplify it, M1 becomes pi M over 16. Can you quickly check that this is correct? I'm not making a mistake here.
ये क्या है सर?
ठीक है. अब M2 क्या होगा?
सर 15 pi m by 16 हो जाएगा.
Yes. So it would be M minus pi 16. ये आ जाएगा. ठीक है. Okay, let's plug everything back in here. Y1, M1, M1 and M2, right? So into this equation. So that would be 0. Just do it and simplify for me, please. I'll just write down the answer directly. So if you, I'll show you the board again. So if you do, come on. If you plug in these values, Y1, M1, and M2, and solve for Y2, so the answer that you would get would be something like this, pi L over 64 minus pi. So just check the steps yourself. So this was a tricky way to avoid the integration. Okay. And the next problem is a thin uniform rod is bent in the shape of a semicircle of radius r. Where is the center of mass? Okay, so here is the problem. So we have a thin uniform mass rod, okay, and we bend it into a semicircle of radius r. Okay, where this is r. All right. Now we need to find out the center of mass of this object. Any ideas? if I take the origin here, what would be the x coordinate of the center of mass? Let's say it's a two-dimensional problem. So let's this x and this is y. What is the x coordinate?
0 हो जाएगा सर.
X would be 0 because of the symmetry. Okay. If you chop this object here with the same amount of mass at the same positions exactly on this side as you have it on this side, you have exactly same distribution of mass, same amount distributed in exactly the same manner on both sides of this line. That's why x is 0. Y is what we need to find out. Okay, and once we find y, then we would have answered the question. All right. So the general formula for y using the integration method is y integration dy dm. So let's say that we take a small piece of mass dm at a position y, okay, and then we add all those positions in the limit from 0 to r, okay, so all values of y. If we add all values of y, then we would have found the center of mass. This also has 1 over m here. Okay, so whenever you have an integration like this, you try to change variables here in such a way that you can find something that you can integrate easily. Okay, so if you have a circular problem like this, let's say that this small mass dm at position y has a finite length dl. Okay, the length of this small mass, okay, dl, and let's say that dl makes an angle d theta at the origin, okay, d theta. So can we write, and the radius is r, so what is dl? What is dl? No one? Come on.
R sin theta.
R d theta. ठीक है, इस तरह का कुछ किया हुआ नहीं आपने स्कूल में? L is equal to R theta.
हाँ ठीक है सर.
ठीक, so this is dl r d theta. All right. So now you can write the small amount of mass dm as the density. क्या होगी इसकी density कैसे निकालेंगे इस strip की? Linear density. इसका total mass divided by what?
L हो जाएगा सर.
Or is this cross-sectional area negligible?
Yes, it's a small strip, yes.
Then divided by length?
Yes, and what is the length of a semicircle?
2r हो जाएगा सर.
Pi r.
Length of a semicircle is pi r. Okay, so density times this small length dl would give me this mass dm. Okay, and then dl को आगे मजीद लिख दें, m over pi r times r d theta. All right. Okay, so we have been able to write dm, r cancel हो जाता है, बाकी constant है सिर्फ d theta की शक्ल में. Okay, but when we plug this back in here, the integration won't be simple yet. Can we find out a quick way to write y in terms of theta as well? y लिख सकते हैं theta की terms में? देखिए ये y कितना है ये, if this angle is theta. Sorry, this is y है, कितना r sin theta नहीं है?
Yes.
Okay. Now we plug back in y. and dm in here. Okay, so r constant है, मैं इसको बाहर लिख रहा हूँ, ठीक है, and inside और पास r है, ये m पहले से है, देन उधर से आपके पास है m over pi and then the integral, ठीक है, and the integral is simply sin theta d theta. अब थीटा की लिमिट्स क्या होंगी? इंटीग्रेशन लिमिट्स क्या होंगी?
0 to pi by 2.
0 to pi all the way here, ठीक है, and then if you integrate, this integration is straightforward. The answer is 2r over pi. Okay. That
सर
is
आप
the,
m over pi का दोबारा एक्सप्लेन कर सकते हैं, वो आपने कहाँ से लिया?
क्या?
सर m over pi का दोबारा प्लीज एक्सप्लेन करते हैं.
ये वैल्यूज दो पुट की हैं इस इक्वेशन में, ये वाली, ठीक है, और ये वाली, तो m और पाई dm से आ रहा है ना, dm की वैल्यू देखें क्या है, m over pi
Okay.
r dl, m over pi r into r d theta, m over pi नहीं आ गया,
Okay.
ठीक है,
Thank you, sir.
वेलकम. All
हम
right.
सर एक सेकंड, आप वो बोर्ड दोबारा नीचे कर सकते हैं?
जी जी.
Okay, thank you, sir.
Okay, so now the last problem that we are going to do, I wanted to the great pyramid at Giza has a mass of some huge mass, 6.6 million tons, I think, million metric tons, huge mass. Okay, and actually numbers are not important here, and its apex or its summit is 140 meters high, 147 meters. Pyramid. What is a pyramid? You hopefully have some idea of a pyramid, right? Something like this. Okay, these the pyramids. So it has a rectangular base. Sometimes the pyramids have square base. So assume that we are assuming a general. So it has a rectangular base. Let's say it has length and width. And as you go up, these edges start closing in. So it's basically enclosed by four triangles, four faces, four triangles, and then it ends in a point. And from the base to the summit, to the highest point, the height is h. Okay, and the question is asking what? Assume that the mass is uniformly distributed over the volume of the pyramid. How much work must the ancient Egyptian laborers have done against gravity to pile up the stones in the pyramid? Make sure to justify your answer carefully. So you see that they have moved all these building blocks of the pyramid. Okay, so and they have done so against gravity. Okay, and if we just ignore that they did not, so the work done against gravity would be very simply equal to the change in potential energy or negative change in potential energy. Okay, so if we can calculate the potential energy of each of these objects, each of these pieces sitting in there, okay, we would be able to answer the question, how much work has gone into building the Great Pyramid of Giza? All right. So what would be the potential energy of a brick sitting here? Let's call that its mass is Mi and its position is Yi. What would be its potential energy?
MIGYI.
MIGYI. Okay, so we know this energy now. If we sum it over all bricks, okay, we would have found the work done. All right, so that would be the work done. And now let's take the G outside, which is constant. Okay, and what is this? MIYI. Let me help you. Okay, let me read it. Let me multiply with this M and divide it with M as well. What is this? What is the object in parenthesis? Isn't it the center of mass of the pyramid?
ये सर सेंटर मैस आ गया.
Yes. So basically, this is a tricky problem. So instead of doing all this sum, all you have to do is, if you can figure out the center of mass of an object like this, then the work done would be simply the work that you have done to raise that point from 0 to y, this point. Okay, simplifies the problem. So the actual problem is not that difficult, meaning getting the potential energy or the work done if you know the center of mass. So we need to find out the center of mass. If we can find out the center of the mass of a pyramid, then we would have answered this question. So let's try to do that quickly. So if we look at the one face of pyramid, okay, this is how it looks like. Okay, a triangle with base length L and height H. All right. Now, but before I do that, let me just write. So what would be, we need to just find the Z coordinate. Okay. Again here, if we take the coordinate system where the center of mass is, okay, then you see, because of the symmetry, if I make my axis, if this is y axis, this is x axis, and if this is z axis, the pyramid is symmetric in x and y. If you chop it from the middle like this, or if you chop it like this from the top, you would have same amount of mass on both sides in an identical, distributed in an identical fashion. But if you chop the pyramid in the middle here, you won't have the same mass, and neither have the same mass, neither have the same distribution of mass in space. Okay, so there is asymmetric in the vertical direction and is symmetric in both horizontal directions, x and y. So if we choose the origin carefully, the x would be 0 and the y would be 0, right? So the only thing that we need to find is z, okay? And again, we use the most general formula for doing it. That would be 1 over m times z dm. Now remember the same exercise we did in the previous problem, that we try to recast these variables in such a way so that we can integrate. All right. And when we were recasting these variables, one of the things we needed was the density. Okay. So, and to calculate the density, we need to figure out the volume of the pyramid. Okay. So how do we figure out the volume?
Isn't it asymmetric along the y direction?
Yeah.
Isn't it asymmetric along the y direction, sir?
इस डायरेक्शन में?
Yes.
नहीं, देखें आप, एक वेज है, ये वेज शेप है, ठीक है, इसको आप टॉप से काटें, ठीक है, टॉप से इस तरह काटें या इस तरह काटें, आप बराबर बराबर हिस्से कर लेंगे। लेकिन अगर यूं काटें ना, यूं, इस एक्सिस के दरमियान एसिमेट्रिक है। वो लाइन आपको इधर नजर आ रही है y के पैरेलल, बट एसिमेट्री इस डायरेक्शन में है, z में। z की वैल्यू डिफरेंट होगी, मिडिल में नहीं होगी एग्जैक्टली। y की वैल्यू मिडिल में होगी, x की वैल्यू भी मिडिल में होगी। All right. So now let's figure out the volume of, so in order to figure out the volume, so the formula for volume is of a solid object like this. So you can generalize. So let's say we take the base of the pyramid, okay? Or any slice of the pyramid here, let's say. This is how it would look like. Right? This little slice. So let's say that it's at a z, this slice is at its height z. Okay. So what would be its length y? And you see length varies depending on where you take this slab. Its y, its length is different. If you pick the slab here, its length is exactly L. If you pick the slab here at the top, its length is 0. Okay. So length y, width x, and height dz. Okay. So what would be the volume of this little slab? X, Y, D, X, Y, dz. Now, if we can add all these slabs, we would have found the volume. Okay. All right. But then again, here again, we have the same problem. We have different variables. We have to figure out how to do the integration. Okay. We need to find out, we need to recast all these variables into a single variable, ideally. Okay. So this is how we do it. Look at this triangle that I am tracing out with the blue chalk. Okay. Now this part is L by 2 and its height is H. Okay. Let's take that ratio. L by 2 over H. Okay. Now look at the second triangle that I'm trying to trace here. All right. So this is now this length, this is X by 2. And this bit here, if this is Z, then this bit here is H minus Z. ये वाली चीज, ये side H minus Z है और ये X by 2 है. Want the two ratios be equal?
Yes, sir, equal होंगे.
X by 2 over H minus Z. ठीक है. All right. So this you can write further simply. L over H equals X over H minus Z. All right. And from here, can you figure out what Z is, what X is in terms of Z? What is
Sir,
X in?
LH minus Z over H हो जाएगा.
L over H into H minus Z. ये हो जाएगा. ठीक
Yes, sir,
है.
ये आएगा.
In a very similar fashion, you can calculate Y, but सिर्फ ये फर्क है. W over H, ये width है, minus Z. ठीक है. So you have been able to figure out X and Y in terms of Z. Now, if you plug them in here, in this quantity, and take the integration from 0 to H, okay, from the base to the summit, The volume turns out to be, remember these relationships. And I leave the integration for you, is quite simple. The volume turns out to be, the volume of a pyramid turns out to be LWH over 3. All right. Now let's write dm, the mass of the little slab that whose volume we just calculated. So its density would be m over LWH by 3 times x, y, and dz, the volume, density times the volume. And now here again, now we bring this here again, either here or there. Now we bring this back into the actual problem. 1 over m, and here we plug in dm, LWH3 इधर लिख दें, and then you have x, y, and there is a z from the formula, so you have z squared, oh no, sorry, just z, and dz. ठीक है, ये अब इसमें क्या रह गया है, इसमें सिर्फ ये रह गया, ये मैथ कैंसिल हो जाएगा, ये कांस्टेंट्स बाहर लिख दें, LWH, okay, and x and y की वैल्यूज जो हमने अभी निकाली हैं z की टर्म्स में वो लिख दें. So that is L by H, H minus Z, W by H, H minus Z, all right, times Z dz. Okay, simple integration. Again, the limit is from 0 to H. Okay, then if you do this integration, encourage you to do it at home. Very simple, not very difficult. The answer is 1 by 4H. बाकी प्रॉब्लम आप खुद कंप्लीट कर लेना, उसका वर्क वगैरह, ठीक है. Z आपने निकाल लिया. That's the center of mass of the pyramid. To complete the picture, it would be 0, 0, 1, 4 by H. And just don't get confused if you see in any book that it is the center of mass of a pyramid is 3 by 4H. Why both answers are correct?
वो टॉप से होगा, ये बॉटम से है.
हाँ, वो ओरिजिन टॉप पे लेते हैं समिट पे, ठीक है. So both answers are correct. Thank you very much.